Hello and welcome to Easy Projects. So today we will take a look at stepper motors, because I'm using stepper motors in the 3D printer that I'm building, and I thought it would be a good idea to explain exactly how they work. So the whole idea of a stepper motor is that it moves in steps, so you can control exactly how much you move the motor in one direction or the other. Unlike one of these brushed DC motors where you just put a current through it and it will spin one way, you can flip the polarity and the motor spins the other way. The brushed DC motor is very easy to use. You just apply a current to it and it spins. The stepper motor, on the other hand, will not spin if you apply a current to it. It will just freeze in position. So now that this is not plugged in, I can just spin it freely by hand. And if I apply some current to it, you can see now I can't spin it anymore. Well, I can if I apply enough torque. These stepper motors have a rating on how much torque they can take before they step over, and that's called the holding torque. In a brushed DC motor we have the brushes and the commutator that will automatically change the polarity of the field windings in order to make the motor always spin the same way around, with the same polarity of course. If you flip the polarity, you'll flip the direction the motor spins. On the stepper motor we don't have that. We just have access to the windings with these 4 wires coming out of the motor. So in this case the red and the blue wire are one coil and the green and the black is another coil. It might not always be like that, and especially with the cheap ones coming out of China, you really want to measure the resistance in the coils to figure out which wires belong together. If you pick 2 of the wrong wires, say the black and the red, you will read almost infinite resistance, whereas if you pick the correct ones, you would read a couple of ohms. So now back to how these motors actually work. So I have drawn the most simple form of a stepper motor that we can make. At least the simplest that is remotely related to the one we looked at before. So what you see here is a rotor in the middle, and that has a magnet on it. So it has a north and a south pole. That would be the rotor you see in the middle of this motor. Then we have these coils, and they are actually only 2 coils. So this will be connected to this, and this connected to this, as I have drawn with these dots in the middle here. So if we energize one of the coils, we will make an electromagnetic field. So say we put a positive voltage here and a negative voltage here. That could make a south pole there, that would give a north pole there, and a north pole here and a south pole there. And you can see it lines up with what's on the magnet, so this north pole will attract the south pole, and this south pole will attract the north pole on the magnet. And this attraction is what is giving us a holding torque, so that if we energize the coil we can't spin the rotor by hand. Now if we want the motor to spin, we want to change which coil is energized. So we turn this one off so we lose the magnetic field, and we turn this one on. If we put the south pole here, we'll get a north pole there, a north pole here, and a south pole there. So that would be something like that. That will now make the rotor spin. So that the north pole is now facing this south pole, and the south pole is now facing this north pole. And we could turn this one off again, and now energize this coil again. But this time with the reverse polarity. So we put the positive here and the negative up here, and that will flip the polarity of the magnetic field. So it will make the rotor spin this way. And if we continue this pattern, we will make the rotor go clockwise. But at any point, we also have the opportunity to make the motor go the other way by going back in this sequence. So now we would, if we wanted it to go clockwise, we would put the positive here and the negative here. But if we put it like it's drawn already, the negative here and the positive here, it will of course go back the other way. So that would be the very basics of how a stepper motor works. But you can see if we complete the circle here, we get 4 steps in 1 revolution. And that's not very good. At least not compared to one of these, which is a standard NEMA 17 motor. It has 200 steps per revolution. So 50 times more than this one. So to improve this, we can do one of two things, or both at the same time. We can increase the number of poles on the rotor, or we could increase the number of coils. We could do something like this, where we still have one end of the coil opposite the other end of the coil. So these two coils, the A and A naught, will be connected, and likewise with the others. In this configuration we have gone from 4 steps to 8 steps per revolution, but we also require 8 wires to come out of the motor. You can see if we wanted to go to 200 steps, this would be very, very impractical. It will be more practical to increase the number of poles on the rotor. We just have to keep in mind that we still want the poles to alternate, so north, south, north, south, north, south. And in a configuration like this, we want the north and the south poles to be 180 degrees apart also. So for example, a 4-pole rotor wouldn't work in this configuration. We can also see that now if the south pole is right here, we would have a north pole here on the coils. If we then energized this coil with a north pole here and this one with a south pole here, it would make the rotor spin like that. Then these two would be placed evenly spaced from this point here. So if we made this a south pole, it would attract this north pole. So we would get one more step. And continuing like that, you can see we now have 12 steps instead of 4 steps before. There's still a long, long way to 200 steps though. And in something like a NEMA 17 motor, it would be very difficult to get 100 poles if we had to do it this way. So they have come up with a very smart way of making these stepper motors that allow them to have 200 steps. I'm not sure I can draw that very easily, so we'll just take this one apart and take a look at the actual rotor and coils inside. There's just 4 screws on the back here. And you have to be a little bit careful when you pop the lids off this, because there is bearings in both ends. So you don't want them to get too crooked when you take them apart. You can use a screwdriver and then gently pry one side, then flip it and pry the other, and it pops right off. And the same for the other end, if we can't do it by hand. Nope. This one is, oh, there we go. That was a little bit harder. And in the back here you have a spring and a washer that you want to keep track of. And now you can just push the rotor out of the housing here. You want to be a little bit careful that you don't get it crooked, because it is magnetic, so it will try to stick to the housing. Now when looking at this rotor, you can see that there's a whole bunch of tabs on these two cylindrical shapes here. And there's this shining disc in the middle. So what this is a magnet with a south pole on one end and a north pole on the other end. And these are just some metal discs. I'm sorry, I can't really focus too good on that, but you can see it's laminated, just like a transformer. So by having the magnet in the middle, they make this whole section a north pole and this whole section a south pole, or it could be the other way around. And if we look closely, you can see that the tabs on these line up exactly with the valleys on this one. So they are spaced one tooth width apart. If we look at the housing here, you can see we have some coils, and there are 8 of them. But they are not in a configuration like this one. It's still only 2 coils. They just go like A, B, A, B, A, B, A, B. So if we get a north pole here, we will have a south pole here, also a north pole there and a south pole there. And you can see the cores of these windings also have the same tabs as is on the rotor. So what happens if we energize this coil with a north pole is that the tabs of this will attract the tabs on the south pole of this rotor, and it will repel the tabs of the north pole. And since these are spaced so that the valley of this lines up with the tab of this one, it wants to go to the same position. Then when we switch to the next coil here, it will only turn it by 1.8 degrees, which gives us 200 steps per revolution. If you actually count these, you will find that there's 50 taps on each of these, giving 100 in total. So it works almost exactly like this one. They've just done it in a more clever way to get enough taps so that we can get the 200 steps. So let's put it back together again. And it's not very uncommon that when you put these back together, that the rotor will kinda bind up in some places. I felt it did it just before. If it does, you can just loosen up the screws and then try and move the back and the front piece a little bit around and then tighten them up again. The tolerances between the coils and the rotor are very tiny, so if they get a little bit off, it can kind of reach. Yeah, that did it again, but it's not much. And you also don't want to over tighten these screws. So I've been spinning this for a few seconds and trying to apply pressure in different angles to make sure that it doesn't bind up. So you might also have heard that there's different ways of driving these stepper motors. What we have been looking at so far is full steps. So it will move one full step every time you change something on these coils. What we can do though is now this coil is energized. If we don't de-energize it before we energize the next one, and we make a north pole here and a south pole there, you can see now where should the rotor go, because it has two options, a north there and a north there. So it will of course go to the middle, so it will put the south pole there and the north pole there. So instead of a quarter turn before, we now only get 1/8 of a turn. And now when we de-energize this coil, oops, I erased the wrong line before. But now it will be like this. And now we re-energize this coil, but with the opposite polarity. So we get the north here and the south there. And now it will spin 1/8 of a turn this way again. So it'll be like that, and so on. So this would be half stepping. And now when we get into micro stepping, it gets a little bit more complicated, because instead of fully energizing and de-energizing the coils, we can also do 1/2 of the current, for example, on this coil, and make a 1/2 south pole here, and we have the full current on this coil. So that will put it somewhere around here, the new north pole. If you get into the details to get this exact, it's probably not 1/2, because I think the forces will be related to the sine and the cosine of the angles that you are working with. Don't take my word for that, because I have not looked into that. But the whole idea is that you do not fully energize the coil, you add a little bit of current at a time. So you change the current from this winding all the way to this winding, and you do that in steps. So you can in theory get as many steps in between here as you want. The only disadvantage is that you lose torque. So generally, if you use micro steps, you'll have less torque than if you don't. So I think this is it for this video, and if you liked it, please give it the thumbs up. And of course, if you have any questions or comments, you're welcome to leave them down below. And until next time, see ya!